you still on 10
We're looking at the very end of 13 and we're going back to 12.
Oh, 13.
Yeah, we're going back to 12. This is page 123.
Alright.
Yeah. Okay, so 12,000 volts. What's the ratio, the transformer ratio there? Let's say what is the voltage ratio? That's the best way because it's really you're tapping into the same number, the same winding. So it's better just to say what's the voltage ratio.
100.
100? Okay, so 100 to 1. It's not recommended to have auto transformers with this huge scale. Usually they're better for small incremental voltage changes, right? Not this drastic amount. You should have an isolation transformer, a dual winding transformer for this application. Here's the hazard that can happen. If this part of the circuit becomes open, right? If it was connected properly, it would run properly. 120 volts, 12,000 in, 120 out. Yeah, it would actually work. But if one of the windings came open, if this part came open, what you have is like a big inductor in series with a resistor. It becomes a series circuit. And what do you know about RL circuits? You get high voltage drop. It's possible to get a very high voltage drop. You have 12,000 volts. Do you think the drop across the resistor is going to be 120?
No.
I don't know what it's going to be unless you play with the numbers, but it's going to be a lot higher than 120. So here's the equivalent circuit that it would look like. And the little dangler, here, the one that's loose, disconnected, would be just hanging here, maybe where my cursor is, just hanging there and not doing anything. But it would be producing voltage as well, at whatever volts per turn, the 12,000 impressed upon the whole thing. So that's the situation you'd have. So now it says the 120 volt load is now subject to a high primary voltage, extremely dangerous situation. So normally auto transformers are used for small step up or step down, not such a large application. It gets disconnected. Right, Alex? So another hazard. Yeah, could you unplug and listen to the lesson with us?
Okay,
thank you.
I'm a little bit lost here.
It's plugged in.
Well, I was lost a little bit. I'm trying to catch up with
Yeah, it's probably good to just listen and then catch up after class. Okay, thanks. A, B, C. Okay, here we got this one. Here's an example. It's not necessarily a high voltage situation, but it's a step down. So let's think about this. It says ratio close to unity. So what they mean, it's close to 1-to-1. 1-to-1 ratio. There's another unity. I don't like using the word unity, but 1-to-1 ratio. So at point X, what's the danger then? Why would this be a problem? It's
because there's still voltage, but it's not being used.
Yeah, what's happening here is, let's say this is 120 volts. Whatever. It could be, let's say the supply was 130 and you wanted 120, so you brought it down a little bit because this voltage was a little bit high. Well, you'd be left with 10 volts being impressed upon this little portion, right? And then this would be a source to that. And it would step it down to 120 volts. And everything is happy and big smiley face and everything until this point also becomes disconnected. Now what you're going to get is this inductor in series with this resistor across, let's say 130. Just trying to make an example here. And you're going to get a lot of voltage across those very few turns. So what you're going to get is a very high volts per turn across that little section, because there's a small number of turns with a higher voltage. You've just shot the volts per turn way up. What happens to the rest of the coil? The higher volts per turn will be times all those turns. So what you're going to get is an extremely high voltage at that connection point when you go to reconnect it. I mean, hopefully you don't do it live, but anyway, so that's a danger right there. So what happens, it says a relatively large current still flows. It sets up a voltage drop across the coil in series with the resistor. And that B to C portion, or A to B portion, is where the volts per turn is now set up, which would be the B to C, normal B to C portion. The B to open portion would be this huge voltage that would be the rest of the turns. Yeah.
So would that mean that since that's in series, there'd be maximum amount of current flowing there as well?
Maximum amount of current.
Yeah.
Through this portion?
It's just
Yeah.
voltage there.
No, zero.
Okay.
It's just voltage.
Okay, so then it, but through A to, because it would flow to RL into A to C would be high because it's the maximum amount of current because they're in series. So,
Well, A to C, it'd still be the 130 volts,
yeah.
but you'd have like a, I don't know, 2,000 volts sitting there, right?
Okay.
You'd produce more voltage out of this thing. It's just a hazard. It's what they're saying, it's a hazard. It says many times larger than the primary source voltage. Okay, so if someone is working live and doing testing or whatever, you might put your meter across it, and maybe it's 1,500 volts instead of 240, or 600, and your meter can't handle it. Only goes up to 1,000. Maybe it only goes up to 600. Blow up your meter. So it could be hazardous. So if the transformer is heavily loaded, right? This is the load. This is like whatever's connected to the transformer. It looks like, hey, this is just a resistor. This is a little transformer. That's what this is. No, that's not what this is. This is a big transformer, and the tech cable goes up to a splitter and a switch, and their main switch could be 400 amps. I don't know, whatever. And so what you're going to get is a high voltage. Now this is, because it's an auto transformer. Okay, and I think that's the calculation portion. So now we're going to go to number 12.
Yes.
I'm going to do this one last, I think, because it's usually where the learning comes in. Save the best for last. Yeah.
So not the best.
Jeff always comes last.
That's why I always come.
That's why we get married. Because I come last.
This is a dual. This is a 600 to 120. Okay, this is a 600 to 120. That's interesting. Okay, so what you're doing here, if I draw a dual winding transformer, just a standard dual winding transformer, you can use a dual winding transformer legally by code. You can use that transformer to act as an auto transformer if you join one of the sides together. It's like you're joining primary and secondary windings together on one side only. If you do that, you're either going to add voltage or subtract voltage depending on which way that secondary winding, or let's call it the low voltage winding, whichever way the low voltage winding is connected, will be either series aiding or series opposing. It's usually because it's drawn as a dual winding transformer that it looks confusing because of the way it's drawn. It's almost like in level 1, they drew a combination circuit and they drew some resistors and then they put a big X in the middle and made some triangles out of it, and well, that looks confusing. So what did you do? You redrew it so that it looked more simple. So you could redraw these, or you could just get used to the way they look, and which is kind of how I do it. But you could always redraw them; it would work just the same. So let's look at the first example. We're going to use a additive one in each case, additive transformer, the same transformer. So let's say I'm using this transformer. You're not physically changing the characteristics of it, you're just using it in 4 different ways. 5 different ways. You could actually use it in 6 different ways. I could use it as a 600 to 120 step down. I could use it as a 120 to 600 step up. or I could use it in 4 different buck/boost configurations. There's two voltages you'll get out of it if you do the buck connection, and there's 2 different voltages you get out of it using the boost connection. Okay? Now, it's not buck and boost. All that means is either you're adding the winding to the other winding, or you're subtracting the winding to the main winding. We'll call the main winding the higher voltage. Just make it easy. We'll call H1, H2. We'll say that's the main winding. And it'll be the prevailing amount of voltage anyway, and all you're going to do is add or subtract to it. Now I'm going to go X, which one? X2 over here?
Yeah.
Okay, awesome. If you connect these two on the left side, I'm going to join H1 to X2, and I have a 600 volt supply. Okay, there's my supply. So that's my line 1, line 2. Have I applied the correct voltage to this winding?
Yes.
Yes. Okay. Have I produced the correct volts per turn? Yes. According, hopefully. Right? So as long as you put the right voltage to the right winding, to the correct windings, then you know that it's going to operate as it should. Okay? This here is the 120 volt winding. Now, what do you know about the 1s and the 2s when you mark them? What is it about the polarity of the transformer that what do the 1s mean? If the H1 and X1, what's the same about them?
They're the same polarity.
Same polarity. So if I give this L1, let's give it a negative. It will be L2 positive. That would mean that X1, because if I'm supplying, just forget this wires here right now, and say, okay, in a dual winding transformer situation, if I were to use it as a step down, this X1 would be negative or positive?
Negative.
Negative. Okay. Nothing's different about that. That's the same. Okay, so establishing that, what I've done here, the source has given us this transformation voltage here. We have 600 volts sitting here, from positive to negative, and we have 120 volts sitting here, from positive to negative. So that means potentially, or potential-wise, I don't know how to term that, but thinking only of the potential, or the polarity, you could say the potential from this point here, if I start here, make that my reference, start there, and let's travel across the windings. I'm going to say I'm becoming more negative by how many volts? At this point. Okay, I'm at negative 600. And now I'm going to carry on, and this is just a wire, and I say I'm becoming more negative by 120, so at this point to my reference will be negative 720 volts. And this will be positive. Positive and negative 720. So that means I can use those two connections as a 720 volt source. I don't know why you want to do that, but I could, right? This would be, over here, a 720 volt load could be connected across those two connections. Now that's what they've done here. They've put RL as the load. So if you go from 2 to 1, 2 to 1, that's called a boost connection. Because we've series aided the two sources. We've aided this source here. This is a source. And this is a source. This winding is not a source. This winding is a load to the source. But the 120 volt is a new source because we've transformed that from our 600 supply. So far so good? Okay, it's weird, but it's good. Eric and then Mike.
What do you mean by 2 to 1?
H2 to H1, X2 to X1.
H2 to.
So we
Okay.
followed the same numbering, so we've gone, and I've chosen positive and negative, so I said, okay, we went 2 to 1 was positive to negative, positive to negative. I could have made it the opposite and got more positive to the other point. I just picked a side, any side. Okay,
Mike?
so that's a boost connection. Let's look at the load. Let's look at the load itself. I think in the book they used 10 ohms or something.
Is that your question? No. Okay. Oh, Ron?
Yes.
Mike had a question.
Oh yeah, I'm sorry. That's not important. Yeah, what's that?
Is it a boost because the 600 and 120 are adding together?
Absolutely. It's only the relation of the two windings. That's why you call it a boost.
Okay.
It's not whether one is a step up or step down supply load. It's not a supply load situation. It's only the configuration of that X1, X2 winding to the first winding, by winding. Your good question. Okay, so they use.
Where's your mom?
Okay, I see what they're doing here. Okay. How would you redraw this? If I were to redraw, if you like, I could say my 600 volt supply is here. Just like an auto transformer, right? And I could call this, let's see, I started up here, so I'm going to call this positive and negative. So this is H2, H1 would be my supply, so let's do it this way. And then the winding would be here. Okay. And then what about the secondary? It goes from X2 to X1.
Yeah, he's starting that.
And where's the load? So if I gave this polarity, we said 2 to 1, all the 2's were positive, all the 2's were positive, all the 1's were negative. Does that look better?
Not for me.
No, that's an auto transformer, the same as we've just done over here. This one's a step up though. It'd be just like drawing a step down auto transformer. It's physically the same, right? This little wire here, joining 1 to 2, is this wire here. The orange wire is the load wires. The windings are the windings.
Well, the windings are the windings.
Yeah, this is our supply.
I do. Anything is not.
So which way does the current go through the load?
What's that?
Which way does the current go through the load?
From the bottom to the top.
Yes, good job.
Full mark.
Hey, you got a pretty good percentage on that one. Half mark, no follow through.
Whoa.
Now listen to us. Okay, so which way does the current go through the 120 volt winding?
From the bottom to the middle.
Right?
Yeah.
Okay. So that means the current goes this way, and then negative to positive goes this way. Okay. And this wire goes this way. Now, this green was just my method of tracing out potential difference. So just that dotted line, you're just moving from one, keeping a reference, going from one point to the other. So I said I'm starting here, my voltmeters going here, I'm 600. Now I'm 720, the load has 720. It's just like two series aiding sources, two batteries. One source is the supply. This is the one source. The other source is the 120 volts. So this current must be going from negative to positive through this portion. But is it? Is it?
Oh.
It's not.
Is it? That's the question. Sometimes we think, oh, it should. It should, but we got to see first, right? All right. We know that it's leaving the source and coming back. So we know that it's doing this and this. I'm pretty safe to say that it's going to do that. Okay, it's leaving the source, leaving the negative and coming back to the positive.
Right.
Right? Probably is going this way. Probably. So let's draw that in and put a question mark.
Don't you have your lead? Nope, I'm lying. Good job. You done good, bud.
Okay. Now, what is the maximum current that each winding can handle? Well, let's give it a kVA rating. Let's see, what do they call it, a 3 kVA? 15 kVA. We're calling this one, on the main page it said it was a 15 kVA. It says right there, 15 kVA. So this transformer is a 15 kVA transformer, 600 to 120. A lot bigger than this one I have on the desk. This is only a 500. So we take 15,000 VA, we say, okay, what is my VA out? So remember the key. The key to solving these is get your VA out. Where do you get the VA out?
You want to divide the
No. Where do you get the VA out?
secondary.
Yeah, well, I don't know what I can handle there. Oh, okay, well then I have to go with the VA in. Yeah, so if I don't know the current here, I don't know the resistance here, they didn't give it to us, then what we're going to solve is how big of a current we can draw from this setup. So I have to go per winding. So now I'm going to say 15,000 VA divided by 600 volts gives me maximum current in each winding. And I think that's the only way to really solve this. So what do we get here?
25 flat.
25 amps?
Yeah.
0.000.
Okay, and this one, 120,
125.
125 amps. So how much load current can we develop? Okay, let's put the numbers in. The key to this, after you get to this point, the second key, which winding is in series with the load?
The one that's lower down.
This one, it's in series with the load. There's always going to be one that's in series with the load. So if this one is a maximum of 125 amps, that means that you can have 125 amp maximum load.
Just add in 25 as well.
Don't look at that yet. No, only look at, okay, Clay, only look at the winding that's in series with the load
No, I was just
determines the load current.
curious if you could do it the same way as the voltage.
And in the other situation, it might be in series with the source. But in this situation, a boost connection, it's in series with the load.
Actually, that drawing you do on the other side shows you that step better then. How do you tell like the amount when it's in series? How you're pointing at right now?
This one?
Yeah.
It's connected.
It's all connected. I can't go anywhere else, right?
Oh,
If the current goes this direction, in this winding, then it has to go that direction through the load.
Yeah.
All this 125 is allowed to flow through that winding.
And then also point right to left.
Okay, it might be. It might be. That was my question mark, direction, right? It all depends. So I wanted to just show you, usually you don't develop a direction on this one until you know the currents. Okay, so this one here says 125 amps. So what's the VA out? Now I can get the VA out. Yeah, 720 times 125 will be my load.
90 kVA. Flat.
90 kVA. Okay,
Oh, that whole thing flat got you guys triggered, didn't it?
Yeah, it's so good.
90 kVA. So is that VA in as well?
Yes.
Has to be.
Equals VA in up at 600 volt side. So the source will draw how much current? 90,000 divided by 600.
150 amps.
150 amps. Okay. From the source and back to the source. So I'm way up here, I'm not anywhere. So we're talking about this current here. And this is 125 amp load. That makes sense?
Yes.
And then you've got 125 amps going back in. I normally don't redraw them like this myself. I just, you can see, if you can see this, you can just leave it like that. Okay, so 125. Now ask yourself, does 25 in and 125 into this node add up to the 150?
Yes.
Yeah, so 150 goes in and it splits. 125 one way, 25 the other. Yeah, so this current direction is fine. That question mark was the direction. Usually it works like that way. How many kVA is the transformer that you bought, that you put down here and you wired this weird configuration? 50. How many kVA is the load?
90.
How many times more can it handle using this transformer?
6.
6 times the kVA of the transformer. The load is 90 kVA. The transformer used is only 15. Yeah. So you've got 6 times the kVA that you can drive with this little 15 kVA transformer. So that's the advantage of using a dual winding transformer. For buck boost applications, you can use a lot smaller transformer for higher VA output. Most of the energy is being conducted rather than transformed. Most of it's just directly conducted. Yeah, okay, that's one example. What do you think about that?
I mean, once you get it, there's.
Okay, we'll do the other example now. The 600 supply with 120 volt buck.
It's going to be different.
Where's the supply? 600? Make sure that you draw the supply wires, especially for tomorrow's quiz. Make sure you draw them where the supply is, because that'll determine, what's going on. Okay, so instead of drawing a subtractive transformer, I drew the additive transformer that you have here, and you do this connection. You put the 1 to 1 and the 2 to the load instead. So you basically flipped it around connection-wise. So we're going to go 1 to 1, and then we're going to take 2 out to the load.
1, 2, 1. They're opposing.
So, what kind of connection is that, Michael?
That is.
Buck.
A buck connection. Yes. Why?
Other, because it's the other one.
It's the opposite of the first one.
Because the lower voltage winding is series opposing the first winding.
My Michael's so small.
And this is what they used on those tanning beds. They used a 240 to 32 volt transformer and subtracted the 32 from the 240, and then you supply it with 208, and you get 240 out. Use the buck connection. Okay, so load. We got to determine what's the maximum current. So this is still a 15 kVA transformer. So each winding develops maximum current. We got that all figured out already, right?
25 and 125.
Let's keep the same potential. Instantaneously there. And this one. Okay, so if I start as a reference point, I'm going to start here as my reference point. And around any closed loop, the sum of all the voltage drops and rises.
Source.
Yeah, equals the source. All the volt rise and drops equals 0 actually, because once you get through the load, now it goes down to where you started again. Everything should add up. All the rises should equal the drops. Okay, well these are voltage rises, and they're also voltage, they're considered voltage drops if you go down in energy and then you increase in negative energy, if you call it negative energy. The yoga people don't like negative energy, but here we're just talking about negative electron energy, so we're okay. So I'm going to start here. I'm becoming more positive. At this point, I'm at negative 600 volts, right? And now I'm going to this point. What is it at this point?
Positive and negative.
That is,
No, positive 120.
So I go negative 600 plus 120,
you're still negative.
negative 480.
See.
That's what I have sitting there. Does that make sense? Do I have to draw it with 2 batteries?
No, that makes sense.
Yeah.
Less than.
Yeah, but it's the difference now between the two. But this is the most negative point in the circuit because this was the most positive point in the circuit right here. I think if you analyze these that way every single time, you'll really understand it. Some people are saying, I'm going to do that. Okay.
Equivalent to haters.
I just do it, bro.
I can do it. I can do it.
And this would be, up here would be 0 volts. So if that's negative 480, then the potential difference between the 2 points is 480 volts across this loop. And because it's AC, it's never negative and positive at the same time, so it's always alternating, right? Okay. 600 volts, 120 volts. Which way does the current go through the 120 volt winding?
Left to right.
Right.
Ah.
Boys. Right to right.
Yeah, left to right. 50, 60.
Is that right?
Yeah.
Well, you know that by establishing this potential difference here, you knew that this was the most negative part across the load. It wasn't the highest negative point in this circuit. Negative 600 was. This is negative 480 and 0. So that would be more negative. The load would flow, the current would flow from negative to positive. So that means that if you follow it along, you know, this wire here, then it has to go that way. Has to. Okay. Which means that it also has to come down this way. So there's going to be a current leaving there of what? What is the load current?
25 amps.
125 amps on the 120 volt side. So 125 amps here. 125 amps here. Is that, you see that? The one in series with the load determines the load's current. Okay? Doesn't matter which way it went through, that just changed the voltage across it. How many VA now? Now you can do the VA out and say, what is the VA out? It's going to be different from the other one because the voltage is now less.
60,000.
60 kVA, okay, 60 kVA out. That's also in. So you take it up to the supply and you say, what is the supply current coming into the whole circuit?
100?
kVA, or sorry, 100 amps? Okay, I think you're right, yeah. It's easy math.
Easy, man.
60,000 divided by 600.
That's the supply.
Okay, so far so good. So into H1, it's 100 amps. Out of H1, it's 125. So what must happen now?
25 amps.
You have to add in 25 amps. That make sense?
Yes.
Sure.
Beautiful.
So that's why you cannot determine the current directions on these things. It's really weird sometimes. Okay. Now, we got 25 amps, 125, and 100 comes out. It also works on that node. Kirchhoff's current law, I was all happy too on each node, H1 node and H2 node. Yeah.
There's also the 600 volt part, also now it just becomes a source of the battery.
It's like a source, yeah. Yeah.
Cool.
It's hard to picture it if you redrew this into an auto transformer. Now you'd be actually stepping down. So this would come in, how would that look? So I took, I'm not going to redraw everything, but you take 600. So that's my supply. This was what, H2, H1, positive, negative. And now we take this point, the H1 point, and connect it to X1. X2, which is negative and positive. So that's what you've done. So what you've done is you've kind of subtract, it's almost like taking it and subtracting it and stabbing it in over here instead. Although you're not doing that, you're taking another winding. It's almost like a battery that's 120 volts, series opposing a 600 volt battery, and now you have only a 480 volt supply left over. It's like your level 1 series sources, series aiding or series opposing. So we did a buck connection, we did series opposing, we ended up with the difference between the two voltages rather than the sum of the two voltages. All right, what's the, how much more load can this transformer handle then? This one was 6 times the kVA of the transformer. And this one is what? 15 times something equals 60.
4.
4 times the kVA. So far that one looks like the best ratio of how small you can build that you could make a transformer for that load. Okay, then we got a third situation. There's four situations, so we use the same one. Let's see. This is H1 over here, and this is H2 over here, right? Yes? And they're diagonal. What's my supply in this case?
600 stuff?
120.
Ah,
Don't go for
no, because it's H.
Applies to low voltage side.
I put my polarities in,
Don't worry, guessing's not from our.
and then we're going to connect it in a boost configuration, are we? Yes? Yes.
At least I'm.
There's actually 8 different configurations because, I'm not going to get into that just yet. Anyway, so 120 to 600. So I'm going to go from 120, and what's my output voltage going to be on this one?
700.
720.
No, 480.
You're
Who
negative.
says,
Oh, wait,
who
hold on.
says 480?
No, tell me.
One
Jeff,
second.
Jeff, Brewer.
I'm gonna go with
720.
Who says 720?
720.
Sorry, Jeff. Try it. It's, so going from this point as my reference, negative 120, at this point I'm at negative 120, and now I'm at negative
right?
720 down here. So this is negative, this is positive, and there's my load. I wish you paid more attention to level 1. Okay, you're all good. I know.
Wait, everyone.
Okay, which direction does
Wait,
it
what
go
did he
through the
say?
600 volt coil?
Left to right?
From positive to
Oh, no,
the left.
to right.
The
Left to
H
right.
is positive, right?
Left to right.
Yeah.
Because the current direction in the load, because this is like negative 720 volts, right? Negative 720 volts and 0 volts. You're at 2 different levels. The current has to go from bottom to top. I'm going to do them all like that, just so we know. Just so we're not comparing apples to apples. Okay. Current goes down this wire, so out of that node right there, out of X1. Okay, how much current? How much current is the 600 volt winding capable of carrying? 25 amps. So now the load can only handle 25 amps in this setup. If we're supplying 120 volts only, that means that the load is now dependent upon the higher voltage windings current instead of the low voltage windings current. Okay, so 25 amps. So 25 amps. Now I can say the VA. By the way, this is 25 amps here. This is 25 amps here. Pretty happy with that. That's how I do it every time. Just figure out which one's in series with the load. Boom, 25. This winding can only carry 25. How many VA is that?
Is that 18K?
18.
1800?
18,000.
Oh, 18 kVA?
Yes.
18 kVA. Out. Pretty safe to say from the source, that's going to be 18 kVA in. Hopefully. Has to be. Energy out, energy in is the energy in. Has to be. Okay, so 18,000 divided by 120 gives me the current from the source. Pretty huge.
150.
150? Okay. Okay, 150. Now I can say to myself, self, 150 minus 25 means that I have to have current going from left to right through that winding of 125 amps. And that is the maximum of the winding. They'll always draw, like you always calculate based on the maximum current in each winding, and then you just figure out which direction they go and make sure it works. 150, 125, 25, yes. 25 plus 125 is 150. Everybody's happy. There you go. So how many times larger kVA is this setup than 15? 15 to 18, not much now this time, eh?
1.2.
It's only a 120 volt source, right? It has something to do with it, right? Okay, so 15 and 1.2 times. So 1.2 times the kVA of the transformer is the load that I was capable of supplying in this case. This is all in your book, it's just, I'm just going through with you on it so you can see it. How I'm dealing with it.
You gotta see to believe it. Alright?
Yeah. Is that a buck or boost connection?
Yeah, which one?
That's
The one we just did over here.
That's a boost. 720?
boost.
Don't look at the voltages because this could have been the supply and that could have been the load. Like,
Oh.
this doesn't matter, you could interchange supply and load in this. You could have a step up or step down on a boost connection. Doesn't matter.
Is that a boost just because they're 80 or
That's right, only the configuration of the windings. Nothing to do with whether you're stepping up from the supply or you're stepping down from the supply. It's got nothing to do with the turbine.
So it's the crisscross then? Like, if you
Crisscross is next week.
it's by
One more.
crisscross.
Yeah.
That's what determines.
One is
Well, if you wire it,
Then we'll do one with the reverse line load,
so
just to mess you up. Okay.
draw it out. So this is going to be butt connection. Yes. I'm done. Thank you. They're okay. Maybe half.
So you think you got this, Clay? Think you got it figured out?
I don't, I'm not choosing to leave, I'm forced to.
No, I know, but, no, I'm just saying.
Yeah, I'm feeling somewhat sharper, but
Okay, great.
I don't think there is a bus that runs from Colonial to Waco. You have to take it in the I'm pretty sure I looked it up first. You have to go where the best way to do it is just bus to the Surrey KPU and then get the school bus to you. Yeah, it's like 2 hours. Yeah, so I know it's like a waste of time to take, right? But it'd be cheaper to take that.
Does the shuttle go between cabins?
I got screwed, I can't get out of this like white rock and like 6:30.
Okay,
Waste like half an hour though. Cheaper than waste so much time.
we'll do the same video here.
This is the butt connection. Preaching to the choir.
Why do I put the polarities on there like that?
Because it helps you with your reference.
Yes. I could use the numbers, and I could say 2, 1, 1 to 2, and know that they subtract. And then I'd be like, okay, which way do I want my currents? I want my currents to go. I think it's just easier to label the polarities,
Negative 480.
personally. You can do it whatever way works for you. Okay, 120. I've got a supply of 120. I'm more negative by 120. The next stop over to here would be, I would have to go through this guy.
Negative
And I'm
7.
becoming positive now. Ooh, I'm more positive or more negative?
Positive.
Positive.
Is it?
It's like 480 or whatever.
It's 480.
Interesting.
Because you minus and
It's
then
like
add
he's
it.
pretending to think notice already.
Hate it when he pretends.
It's weird, right?
Like negative 120 and add 480, you're kind of like add 600 to get 480.
If that's my reference, I'm getting more negative by 120. So I'm going to say, okay, this part is negative 120 volts. Then I'm going to go down to here. I'm still at negative 120. Negative 120, plus 600 is positive 480. Well, that's weird. So in this one, in this example, I'm actually, at this point, I'm at positive 480. So this would be the negative part of the load circuit. This is the most positive part of the supply, but that's the most negative part of the load circuit. So that means the current must be going this way. Okay, awesome. Okay, so what current is that? Well, we got the maximums on the windings. This was 25 and the other one was 125. So this is going to be 25 amps. Why is that?
480.
15,000 or 15 kVA divided by 600 volts.
Yeah. So the current would go this direction through the winding. Right? And then back up into there, 25 amps. That's why I do it with polarities. It helps me to see where in the circuit this thing is connected. Is it supplying it or receiving from it? Right? Okay. All right, now this is 125. And that means that the 125, we have to figure out what's going on here. I got 25 amps leaving, I gotta do VA out. So the next stop, again, same method, VA out. What is the voltage? 480 times 25.
12. K.
12 kVA?
Yeah.
12 kVA. And that's in equals out. Arrow up to here. So 12 kVA in divided by 120 should be 100 amps. Nice easy numbers.
No, wait. Oh, yeah.
Down there, is that the correct way from the source for the 100 amps? Those,
Yeah.
I think so. I'm gonna go. Okay, 100 amps in, 100 amps out. And now 100 amps goes into this node at X1, and 25 amps goes in at X1, and that means that I'm going to have 125 amps going that way. And you got to make sure it works at X2. The 125 goes in, splits out 125. Yep. Check. What's the kVA ratio between what went out versus what was versus the rating of the transformer?
0.8 or something.
Yeah. Whatever 12 out of 15 is.
0.8%.
0.8 times the kVA. So now it's actually not an advantage other than the voltage that you wanted. All right. Questions on that?
What? What connection is that?
But,
So if you follow it through, they show you what's actually happening with simulation using a battery as your potential.
For loads, did you ever ask us, you know, would an answer always, because it's like, in one side it's negative 480 over there.
Yeah.
Would you ever ask us for a negative answer? Like,
Not usually, it's just, it's AC, so
okay.
just what's the voltage across the load,
Oh,
right? You know you can add or subtract. Was that one a buck or boost connection?
but
Buck connection. Okay, what if I supplied 480 volts and I got 120 volts out of it? Would that be a buck or boost?
so was that again?
My supply, say I put my supply here and my load up here.
480.
I had 480 volt supply and a 120 volt load.
That's gonna be
Be still buck.
It'll be a buck. It's nothing to do with step up or step down.
Oh, yeah, you're wrong.
Everything to do with the configuration of this winding compared with the winding it's in series with.
For the load to figure out the polarity, do you just do the positive 480 and then the other side's connected to where I guess 0 volts would be? So the 480 is just more positive than 0?
Yeah, yeah, but it's more positive. You become more positive than where you started. That was my reference, 0, yeah. If I put 0 there,
Yeah.
yes.
Okay.
Yeah, that helps you. Because you're establishing a reference point, you're saying, what am I now? What am I now? What am I now? Right? That's really all you do. What's up?
I have a question to that. You always
Little tiny, that's
Yeah.
where you're at.
Yeah, because it's positive 480 on the bottom of the load. And the other side of the load is connected to the ground, which is 0. So therefore negative on the top.
I got it,
Plus
yeah,
480
but
is on the bottom.
getting confused.
Think about what is
This one is in the middle. You have negative 480 connected to that same 0 volt.
Yeah.
Which is like.
Negative 40 is obviously more negative, so then the positive is at the top. That's my question. I just want to make sure
Okay, cool.
the reference is always 0.
Yeah, you put a little battery pack in like the side.
I mean, then
Here's 0. You would start with 600.
It's a little slip.
Monday's going to be fun.
Yeah, then, I know my buddy bought it for me for Christmas, but he's definitely
it's like a reactor.
I just want vectors.
Page 112. 112.
you have what's called a series winding. Usually it's the lower voltage winding because you're making small voltage changes to your load. So we have on page 111, 112, it talks about boost buck voltage regulators. 111, 112. You can also have one that's an automatic type. So it automatically senses the voltage and will automatically adjust the on-load tap changer of the buck boost auto regulator. So the series winding, they label it X1, X2 here. And you can put this selector switch to either boost or buck. All it does is it reverses the way the current goes through the winding. It either goes from 1 to 2 direction or 2 to 1 direction. So boost would be, so I'm going 2 to 1, and this one is going 2 to 1.
Do they normally come in like one with a switch like that, or?
You wouldn't even see inside. It would just be like, here's your selector. You know,
Yeah.
It's like a mount this piece of equipment, and after your, it's not transformer.
But
Yeah.
is that like a usual thing, is to have both a switch with the bucking boost, or is it usual to just have a boosting trans or a bucking trans?
Yeah, I don't know.
Okay.
I don't know. Yeah. Let's go on with the diagram.
Yeah, no worries, I was just curious if that.
Yeah, it's good questions, and Google is your friend on a lot of that stuff. 1 to 2 is the high voltage. So if you're producing a certain voltage, or you have primary lines, and you want, say it's for hydro. Let's say it's a hydro's generating station, and they need to adjust up and down a little bit here and there. They're not going to throw on a tap changer onto a dual winding transformer and change the primary taps every time. Here's one with secondary taps, but instead of using it as a dual winding, you got the same high voltage produced, except you're adding a little bit or subtracting a little bit from the high voltage, and you're still at the high voltage. Okay? So this little gig here, what's the deal with having a reactor in series with 2 switch contacts? Do you remember that part?
The no tap?
So that it's like one's like supplying the difference while it's doing the make or break, so that it doesn't work.
Right, but wouldn't they arc if they went straight across and they had 2 different,
No.
like say there's a 100 volts difference.
They have like a neutral almost kind of deal that the aids or
Prevents it
I
from.
don't know the correct terminology.
Well,
Magnetism.
just like if we redo that the same way as the other diagram we looked at, it's the same thing. And we center tap this as the way in, so if the current had, let's say we had 100 volts here. I don't know if you guys can see this. Say we had 100 volts across there, from negative to positive, instantaneous polarity. Just roll around my chair. No. Okay. So if this was just a connection, we'd have a short circuit from here to here of 100 volts while it's switched. You don't want that. So what you have here is the current here, because the current is going the same direction, it will allow a small current, because what happens is if the currents are going in the same direction, it produces high what? XL, high XL. Because you have counter EMF now, if you have the currents going in the same direction, it produces flux that opposes the current that's trying to change. So now you've actually limited the arcing current between the 2 currents. Now, what happens is when you finally get to the same point where there's 0 potential difference, if you have 0 potential difference between there, you could be on the, I don't know, whatever tap it is, letter C there. There's no difference between those 2 arrows. And that means that the current, though, would be sharing equally from that tap. And so it's this canceling of the flux that actually causes this only to be the resistance only. That would be 0 ohms of XL and only a small resistance. And we're talking like milliohms, hopefully something really, really small. Like a switch, you want to be close to 0 ohms. So that would cancel the flux, and you'd end up with just resistance of the wire. distance of the windings. So they use a reactor on there and they'll center tap it. We have 2 switch contacts. Okay, so having established that then, what would the voltage be if I went from, let's try letter C. What's the voltage right now? Is it adding, how many turns is it adding here? Adding or subtracting?
Right now,
Can you see it? I don't know.
did I go back to it? When it's on C,
Yeah, don't look at the chart.
I don't look at the chart.
There.
I don't think that's possible.
That's the secondary one. That's the secondary lines down there, and that's the primary lines up there. All right, I made it as big as I can.
What's on the second one is?
102.
Okay, so it's on boost. So does it add or subtract? Okay, it adds. So we're going 2 to 1, 2 to 1. So we're going to go to letter C. That goes to here. So we're adding 1, 2, 3, 4 of those little windings.
4, 1,
Aren't we?
1, 2, 3,
Yeah, 4.
4, yeah.
Where would you use all the winding? What letter? You want to add the most possible voltage you can.
A?
Letter A. Yeah, letter
A
A.
goes right through the whole coil, right?
What does letter F do?
The shortest.
Not much.
It's
Yeah.
one winding there, right?
Okay. So I think, yeah, that's weird. So do they have any point where there's zero?
No.
Zero of the windings? Not really. Okay, so I guess they're always wanting to boost. Okay, what if you wanted to subtract some voltage off of there? What if the auto regulation happened that it went, you put it to buck and it was, the voltage was too high and it wanted to subtract a little bit off? So what would letter C do?
It would be the
Letter C would
middle.
take away 2, didn't it?
It would only take away these 2 on the right.
Yeah.
Yeah, or it would only, yeah, it would only deduct that portion. That's right. And that goes straight down. This is the secondary down here.
So from left to right is still like the small to the biggest. Or just, you know?
I'm looking at more turns, add more voltage. So then I can,
More turns.
and then it gives you, so it's telling me the buck position at A is 100%. There is no boost position at 100, so the buck position at A is 100%. So let's see. A, let's see, does that work?
Yeah, because it's all of them together.
There it is, it's direct, it's the only one that will give you 100%. Okay. It's pretty easy, right?
Do we need to remember that?
Do we need what?
He,
Do you remember
yes,
these
yes,
things?
yes.
You need to remember everything.
Everything.
Everything, you won't even, it's all up here. I think the principle.
So,
Principle.
Gonna be with them.
Let's see if I have an example.
You have to remember A equals 100%. And C equals 99.
you have to remember. No.
Just
Yes.
gonna let you guys work on stuff now, I think. Do the best. Yeah, just give you the last 15 minutes.
The imagery is cool.
I gotta go play.
Make sure, yeah, number 1 on self-test 12 is a nice one. I would try to solve everything you can about those 3 diagrams.
Well, someone already did mine.
Did you?
It was me.
Okay, remember what I said though? What if I had a 480 volt supply? What if I made my supply here
Now your load there.
and my load there? Would that be allowed?
Sure.
Yes.
All of it happened.
Yeah, 'cause it's still the same
The
circuit.
currents would be the opposite direction. Right?
Yeah, 'cause it's coming out of the supply and going to each one.
Yeah, and all the currents would be the opposite direction. Right now, this is conventional flow.
Directions still switched up.
Yeah, but you can, it will work either way it will work. But this is the supply and this is the load. I'm not going to share all the values.
So the arrows also don't matter. Yeah. So the arrow, like,
This is.
Yeah, see, it doesn't matter which way you connect them,
60 times a second.
but the currents will change.
Right?
Because
Oh, but it's gonna lag.
I guess
It'll lag.
I don't know. If you switch those, because it's AC, would the current just switch back and forth?
Like the arrows are gonna be constantly switching, right?
But this
But like-
is instantaneous, we
Yeah,
have to.
but the way I've drawn the polarities would mean
Yeah.
that that instant all the currents would go.
Okay.
Yeah, but it'd be the same math,
Yeah.
exact same math.
It's gonna switch 6 times.
Try it out, I mean, you write that one out with your,
Or switch 30
Why?
times.
yeah, so you'd actually have to plug with your.
60 hertz.
Yeah.
Do we need to know that?
No, they're just kind
Oh, here we go.
Absolutely, that's